So let's move on to lecture one, introductions to differential equations. So this is where most of the terminologies related to differential equations get introduced. In this lecture, we're going to understand what a differential equation is on the perspective of definitions. And as I mentioned in the last lecture, in the conversation in the last lecture, it depends on the type of differential equations, and you may have a different solution technique. So the first thing when you see a differential equation is, can you identify or can you classify the differential equations? And because if you are able to classify the differential equation into different categories, it's allow you to pick out a correct solution technique to get the solutions. Right? So here we learn about differential equation and also learn how to identify and classify differential equations. Can you identify dependent variable, independent variable from a differential equation, and what is the order of differential equations? Can you classify differential equation as a linear differential equation or non-linear differential equation? Is it homogeneous or non-homogeneous? And is the differential equation with constant coefficients or with non-constant coefficients? So things like this we need to be able to classify because we need to be able to choose the correct solution technique. So first thing first, what is the ordinary differential equation? So an ordinary differential equation. So usually I just say ODE stand for ordinary differential equations, or DE for differential equations. There's another type of differential equation. It's called partial differential equation. It's called PDEs. Again, that is for the higher level math courses. But for an ordinary differential equations or an ODE, states the relationship between an unknown functions of one variable and its derivatives. All right. So you, in a way, have seen differential equation even in calculus 1 and calculus 2, because you have an equations where you have derivative in the equations set that equal to something else, right? Then that is the differential equations. So in this case, the unknown functions mentioned in this definition is the dependent variable. And the one variable get mentioned here is called the independent variable. So this, when you look at the equations, if you have derivative in your equations, that is the differential equation, basically. Now, some of the important differential equations that you may have encountered before. The first one is the very famous Newton's second law. That is the total force equal to mass times accelerations. And you see that there is no derivative involved in this equation. But remember, accelerations can be written as the second derivative of the position function. So in a way, F equal to ma can be written as m times x double prime, right? For x is the position function, and a is the acceleration function. Right. And because a is written in terms of the position function, in this case, a is equal to x double prime, that is the differential equation that you see right now. And this is called the second order differential equation because the highest derivative in the equation is 2, right? Or the second derivative. Another one is Newton's law of cooling. You have T prime is equal to negative k times T minus T sub A. I will have the similar equations later on when we learn how to identify the dependent variable and independent variable, so I'm not going to write down too much detail here for this equation. But for this equation, T prime is, again, the rate of change or the instantaneous rate of change. K, it's just some constant, depends on the materials that you work with. And T sub A is the ambient or the surrounding temperature. So now in the morning, you make yourself a cup of coffee, a good hot coffee, right, or the hot chocolate, and you leave it out in the room, right, for a few minutes or so. And eventually, the hot coffee or the hot cocoa the temperature will come down to temperature of the room, right, or the room temperature. So that whole process can be described using Newton's law of cooling. Okay. You have a negative here in these calculations because you want the rate of change of the temperature to go down. Right? Um, all right, so another applications that you're going to see in differential equation is the exponential growth. So a lot of exponential population dynamic get used a lot, even though it's not realistic because for exponential growth, these solutions go and tend to infinity as you let t go to infinity. But it's still a good model at the beginning when you talk about how the population increase over time. But for the long run, this is not a good model to have. Okay. So exponential growth model has the form of dp dt equal to r times p, for r is the growth rate. Because it's the growth rate, it has to be a positive number. Exponential functions, exponential growth, the solution of this differential equations will give you an exponential function. When we get to separation of variable in about two lecture, we will solve this particular equation and you will see the solution that is going to be an exponential function. I also have a graph here to illustrate that part. That is, these are the exponential growth model. You have some annotation here indicate y sub 0 equal to 0.5, y sub 0 equal to 1, y sub 0 equal to 2. This is a different initial conditions. Let's say initially the population is this, eventually how is population growth with respect to exponential growth model. And this is a differential equation. This is the first order differential equation because the highest derivative is equal to 1. You have, again, because exponential growth model is not really realistic in reality, right? No population can grow to infinity. We have something more plausible and more realistic. It's called the logistic growth model. And the model has the form dp dt equal to r times p, originally like the first few value of time t will behave very similar to exponential growth, but eventually when you let t go to infinity, it will reach something called the carrying capacity. So multiply with 1 minus p over k, capital K for capital K is going to be the carrying capacity. So k is the carrying capacity. So if you get to when you take the elevator, you see on the side of the elevator, they say have the tax, say the carrying capacity, the maximum number is, let's say 100 or 2,000 pounds, something like that. That value is the carrying capacity. Okay. In logistic growth, first part of the logistic growth behave very much like exponential growth, but as times progress, you have this part to illustrate that, okay, you need to have a cap, right? You cannot go over to infinity. And this part right here is the carrying capacity. Right. So this is the graph to illustrate the logistic growth. And this dashed line is the carrying capacity. So no matter what initial values that you have, eventually everything, all the curve will reach the carrying capacity. Okay. And it's true in terms of populations, right? When you have, let's say, I'm staying in one area, let's say in Bridgewater State area, and you have a lot of students going to the area, their parents show up for orientations, and all of a sudden there's the population increase very quickly, and then eventually we cannot occupy more people, so we reach the carrying capacity. When we reach the carrying capacity, we need to do something else in order to reduce or to balance out the populations, something like that. Now, if you want to take into account an even more realistic model, you talk about logistic growth with a threshold. That means if the population stay above the threshold, everything will reach to the carrying capacity. If the population, for some reason, dip below the threshold, the population will die out, unfortunately. And this can be described using another differential equation, another first order differential equation. Of course, it's very similar to the logistic growth. we just need to add another term into this model. So you have the PDT to illustrate the first order differential equations. You have R times P behave very much like exponential growth, multiply with 1 minus P over K. This is the logistic growth. Now you need to add in another term that is 1 minus P over capital T. So this extra term say that if the population dip below the threshold, the population will die down. So if you see the last graph here illustrate the differential equations, this top dashed line here is the carrying capacity. And the one below this, you have this right here, this dashed line right here. That one is the threshold. Okay. We will see when we get to a different the solution. Sorry, when we get to the solution technique, I will show you the solutions of the exponential growth model, probably the solutions of the logistic growth model. And in differential equations, we can solve the solutions using analytical technique, like integration technique, and other solution technique. Right? However, there are some differential equations that is impossible to get the solutions. And one of that is the logistic growth with a threshold. Right? Even though they look similar to logistic growth, similar to exponential growth, but there's no analytical solutions to the logistic growth with a threshold. And therefore, we need to observe this solution under something called directional field. Okay, and this is the kind of the vector field that we're going to see, we're going to observe, and we get the idea of how the solution of this differential equations behave. Okay, but that again for later. So when you work in real life, in the industry, in the real life example, all of this information is usually get encountered. During COVID, when you read newspaper, they talk about the number of infected cases increase exponentially. When they talk about that, they talk about using exponential growth model. And eventually, the curve of COVID-19 infected cases kind of flat out on the top because they reach the carrying capacity. So a lot of things that you need to do in order to pick out the correct solution technique. Right? Again, the first one is that can you identify dependent variable and independent variable? Let's do something like that. So I have this differential equations, x prime equal to x squared plus t squared. So even though you don't see derivative with respect to something, this is assumed in a way that x carry the prime is going to be the dependent variable. Okay, so x is the dependent variable because the x carry the prime. Okay, and the function with respect to t, right? So x is a function of t, therefore t is the independent variable. So here, quickly, the independent variable or the input is t. The output or the dependent variable is x, and the derivative is x prime of t. Or there's other notation that you can use. So this is, again, the prime is the Lagrange notations. You have the x dt is the Leibniz notations. You can have x dot t, this is the Newton notations. Okay, physics major or engineering major, they tend to use this as well. You may not encounter them, but they get used. So when you read the textbook, when you read some document and you see x dot or x double dot, that is illustrations of the demonstrations of derivatives. So this differential equation is the first order differential equation because the highest derivative is 1. Now I'm going to move on to example 3. I have the example of d squared y dx squared plus 3 times dy dx plus 7y equals to 0. So this is the second order differential equation because the highest derivative is 2. Right? So this is clearly state that you take the derivative of y with respect to x. So it's easier to identify the independent variable and dependent variable. Right? So dependent variable in this case is y, and the independent variable is x. The derivative you see here is d squared y dx squared. So stand for the second derivative of y with respect to x, or you can just do y double prime of x. or you can use the Newton notation to y double dot of x. Okay. Now let's talk about Newton's second law. Let's identify again the input variable or independent variable, the output variable or the dependent variable, and the derivative. So this second Newton's law is the equation describes the position of the particle in time t with mass m under the influence of the force F. Right? You see this in the physics courses many times already. So the input variable here, or the independent variable here, is the time variable. Okay, so t is the independent variable, and x position functions going to be the output variable. And the derivative here is x double prime of t. I just want to write this down a few more times so that you can get familiar with the process. So x double dot. Now for the Newton's law of cooling, we see this equations earlier. So T prime is equal to negative K times capital T minus capital T sub A, for T is the temperature. T sub A is the ambient temperature. Sorry, capital T is the temperature of the object. Okay. K is the positive constant of proportionality. Okay. So input variable here, even though we don't see the input at all, right? But we can assume that this is related to cooling process, right? So you have an object, the hot object, and you want to let it cool down and reach the room temperature. So in a way, we can assume that the independent variable is time t. Right? So little t is the input variable or the independent variable. And the output variable is the capital T letter. Right? It stands for the temperature of the object. So here the derivative is t prime, let's say of little t, or capital dt dt, or t dot of t. So now we need to classify the ordinary differential equations. So we use 4 different categories to classify differential equations. The first one is the order of the differential equations. The second one is the linearity. Is the differential equations linear or nonlinear? The third one is it with constant coefficients or with non-constant coefficients. And the last one is the homogeneity. Is the differential equations homogeneous or non-homogeneous? So the first one is the order of differential equations. Right? So again, it's the highest derivative in the differential equations. Right. So it's a very straightforward category to classify. Um, in the mathematical formula, the differential is written in this way. So in other words, mathematically, you can write d to the power n, sorry, dny dxn is equal to f of x comma y prime comma y double prime dot 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 up to y to the n minus 1, indicate the derivative. Okay, and because the highest derivative in this case is n, this is the nth order differential equations. Sin n is the highest derivative. This equation is an nth order differential equation. So D stands for differential equation. Now the second category, linearity, you want to classify if the differential equation is linear or nonlinear. So how would you do that? When you look at the differential equation and you pick out something called the product of dependent variable with itself or its derivative. If there is something like that, you automatically classify the differential equation as nonlinear differential equations. So the product of the dependent variable with itself or its derivatives. Right. So for instance, for example, if you see something like this, y times it by itself, y times derivative, y times another derivative, something like this. If you see one of this in the differential equation, you can say the differential equation is nonlinear. Another way to classify a nonlinear differential equation is that the function of dependent variable is nonlinear. So for example, you have function line cosine of y, you have sine of y, you have e to the y, you have ln of y. Otherwise, the differential equation is linear. Right, so let me do a quick example. We have a bunch of examples later, but let me give you the example for this particular category to work with. Let's say you have the differential equation of the form y, 1 minus y times y prime plus 2y equal to e to the x. It's a nonlinear because of this product right here. Right? So y times y prime, so that's the nonlinear. I'm going to give you another nonlinear differential equations to observe here. You have d square y dx square plus psi of y equal to 1. Right. So this one is also the nonlinear differential equation because the dependent variable y here has the function of the dependent variable is a nonlinear function. This is a nonlinear function, therefore you classify this as a nonlinear differential equations. Let me give you another question here real quick. Is this linear or nonlinear? It is linear, right? Because you have second derivative, right? It doesn't multiply with another variable. The cosine of x here, even though it's a nonlinear function, but it's the nonlinear function for the independent variable. So this is the linear differential equation. So let me write down here nonlinear. This is nonlinear as well. But the last one is linear. Now the next category is the constant with constant coefficients or with non-constant coefficients. So dependent variable and its derivative multiplied are multiplied by constant. Therefore, you classify this as constant coefficients. Otherwise, the differential equation is with non-constant coefficients. So that's the third category. We get to the solution. We get to an example later. For homogeneous or non-homogeneous differential equations, the dependent variable and its derivatives are set to one side of the equation, and you have the case of 0 on the other side. When you have 0, this is called the homogeneous differential equations. Or anything else but 0. This is the case of non-homogeneous. On the other side. So when we get to the example, I will give you a more straightforward example to work with to classify differential equation, but also some of the trickier questions for you to manipulate it so that you can get to the correct classification. Move on to the next example. I have a bunch of problems here that we can work with. So there are four things that you need to classify, right? Indicate what is the order of differential equations, the linearity, the constant with constant coefficient or non-constant coefficients, and the homogeneity of the problem. Okay, so A, what is the order? Very
So
straightforward.
first order.
First order differential equations, yeah. So the dependent variable always carry the prime or the derivative. So the dependent variable in this case is y, and the independent variable is t. So with that information, let me know that is that linear or nonlinear differential equation. It's actually linear, right? So let's take a look at this. So this is non-linear, but for the independent variable, so that doesn't count. So y prime by itself, product of dependent variable with itself with its derivative. Y in a way doesn't multiply with dependent variable or with derivative. So these are the linear terms. Therefore, you classify this as linear differential equations. Does that make sense? Any, good? Now, is this with constant coefficients or with non-constant coefficient?
Non-constant.
Non-constant coefficients. That's the answer. Because even though, yes, the derivative multiplied with 1, which is constant, but the y is actually multiplied with 3 times t squared, that part is a non-constant part. Because of that, you classify this as a non-constant coefficient. So with non-constant coefficients, CC means constant coefficients. The last one is this homogeneous or non-homogeneous?
Non-homogeneous.
Non-homogeneous. Now, B, what is the order of the differential equation?
That is a fourth order.
Yes, fourth order differential equations. Is this linear or non-linear? Esther, you want to take a shot at this?
Yes, for a second. Non-linear.
Non-linear? Why is that the case? Do you mind me asking?
Because y squared is a product of the dependent variable by itself.
Yes. Yep. So this is a non-linear term. And because of that, you have a non-linear differential equation. This with constant coefficients or non-constant coefficients. So this is with constant coefficients. Okay, because again, take a look at this. This is the fourth derivative multiplied with 1 in front, so that is constant coefficients. Y squared multiplied with 1 as well, so that's constant coefficients. So we classify this as constant coefficients. And everything's, right, all the dependent variable and its derivative gets set to one side of the equations, and then on the other side you have 0, so this is called the homogeneous differential equations. So C, let me quickly do this, C, D, and E. I'm going to do C, D, E, and F quickly, and then G and H will spend a little bit of time, right? So hopefully you get familiar with the process, and but stop me if you have any questions, okay? So this is a second order differential equation because you have 2 dots on the Y. Second order here. This one is linear differential equations, right? And this is with constant coefficients, and the last one is a homogeneous, sorry. Any questions on C?
No.
Good. Now D, this is the second order as well. This is linear differential equations, even though, yes, I have a non-linear terms, but this is with respect to the independent variable, so it doesn't count. So it's still a linear differential equation. And this is with non-constant coefficients, right? Because, yes, this is multiplied with 1, that's constant, but y sub t multiplied with a non-constant. Therefore, this is non-constant coefficient. And everything, so dependent variable and its derivative set to one side of the equation. On the other side, you have 0. So this is homogeneous differential equation. So for E, you have second order differential equations.
I'm sorry, I have a question.
Go ahead.
For D, what does y sub t mean?
Oh, the derivative, the partial derivative.
Okay, so it's for the first term will be like the partial derivative of y with respect to t
Yeah.
twice. Second order. Okay.
Yeah. So second
Got
order
it.
partial derivative with respect to t. Now for e, this is the second order as well, and this is a nonlinear differential equation. The nonlinear term is here psi of y. It's a nonlinear term. This is with constant coefficients. And this is homogeneous differential equation. F, so you see this already earlier. This is first order differential equation. This is a nonlinear differential equation due to this nonlinear terms right here. So y times y prime. This is with constant coefficients. Right? Why is that the case though? Even though you have y prime multiplied with 1 minus y. Remember, the y times y prime is stand for linear or nonlinear. Okay, so if you distribute y prime, you will see y prime minus y times y prime plus 2y equal to e to the x. So y prime times 1, that constant. Y times y prime, this stands for the nonlinear terms. And then this nonlinear terms multiply with 1, so that's still constant. Y times 2, that's constant. Therefore, this is with constant coefficients. Now, the last category, everything dependent variable and its derivative set to one side of the equations. Everything else on the other side. That everything else is different from 0. Therefore, this is non-homogeneous differential equations. Now for G, you have e to the x times dy dx plus 3 times y equal to x squared times y. If you notice on the right-hand side, you still have a dependent variable, and therefore what you want is you move all the dependent variable and its derivative to one side of the equations, okay, before you do the classifications. So when you move that, this is the new equation you got. So this is the first order differential equation. It's a linear equation. So let's walk through this. So dy dx doesn't multiply with dependent variable or another derivative. So even though it's multiplied with e to the x is for independent variable. So this is linear still. 3 times y, this is of course linear. And of course x squared times y. So the x is still independent variable, even though this is a nonlinear, x squared is a nonlinear term. But y multiplied with independent variable. So still is a linear differential equation. Is it with constant coefficients or non-constant coefficients?
Non-constant.
Non-constant coefficients, very good. The last one, because you need to move everything related to dependent variable and its derivative to one side of the equations. On the right-hand side, it's going to be 0. Therefore, this is the homogeneous differential equation. Now, the last equations, dx dt equal to a fraction. So it's not, we cannot just classify this without doing a little bit of work. Okay. So the dependent variable in this case is x, the independent variable is t. So instead of a fractions written in this form, I'm going to write or manipulate these equations a little bit. So here I get dx dt equal to 1 over 1 plus t squared times x plus 2t over 1 plus t squared times x plus cosine of t over 1 plus t squared. So you have a big fractions and you rewrite that in terms of smaller fractions. Now again, x is dependent variable and t is the independent variable. For the dependent variables, I'm going to move everything to the left-hand side of the equations. So I have dx dt minus 1 over 1 plus t squared times x minus 2t over 1 plus t squared times x equal to cosine of t divided by 1 plus t squared. All right. So now at this point, you can technically classify the differential equations. And this is the first order differential equations because the highest derivative is 1. Is this linear or non-linear?
Linear?
It is linear. Okay, good. It is linear. And constant coefficients or non-constant coefficients, Taru?
So we have a non-constant coefficient.
It is non-constant coefficients. And the last one, so again, the definition is that you set dependent variable and its derivative to one side of the equations and everything else to the other side. And everything else is different from zero, so you classify this as the non-homogeneous differential equation. All right. So that's it for me for today's lecture. So in this lecture, we talk about definition of differential equations. So the differential equation is the equation that states the relationship between a unknown function or dependent variable with the independent variable, right? And of course, in the equation, you have some derivatives as well. We go over some of the common and more famous differential equation. We talk about second Newton's law of cooling, exponential growth, logistic growth with the threshold. We learn how to identify the independent variable and dependent variable. So that's a key point for you to further classify the differential equations. We learned that to classify the differential equation, you need to follow four categories. What is the order of differential equations? What is the linearity? You want to classify if the differential equation is linear or non-linear. And you want to know if the differential equation is with constant coefficient or with non-constant coefficients. And of course, you want to classify if the differential equation is homogeneous or non-homogeneous. Again, we do all of this because we want to pick out a correct solution technique to get the solution of the differential equations. And you will see for the rest of the semester when we learn about different solution technique, it will give you an idea of, okay, this is the solution technique for, let's say, a second order differential equation with non-constant coefficients and non-homogeneous, something like that. All right, so that's it for me today. Thank you so much for being here today, everyone. You have a good day, okay? Let me know if you have any questions.